Traffic delay, everybody. So this is part 2 of class 11 chemistry, the same chapter, that's chapter number 1, some basic concepts of chemistry. Now when we finish with this part, in fact the learning objectives are at the end of this lesson or this part, students will be able to understand and explain Dalton's atomic theory. Then students will also be able to understand and explain atomic mass units. Then after that we will have molecular mass, formula mass, average atomic mass, and then students will also be able to work out some numericals of problems based on the same. Students will also be able to understand, define and explain the concept of molar mass, and also work out some numericals and or problems, I should say, based on the same. And finally the students will also be able to understand and explain and also work out some problems or numericals on percentage composition. So now to begin with, we're going to start with Dalton's atomic theory. Now in fact we have studied a little bit about this Dalton's atomic theory in your lower classes, maybe in class 9. Here the theory says that matter consists of indivisible atoms. Well, you remember an atom is the smallest particle of an element which is indivisible. You remember studying about atom in class 9, and this is what this Dalton's atomic theory says. The very first is matter consists of indivisible atoms. In fact, this has its limitations because today an atom is known to consist of its subatomic particles like protons, neutrons and electrons. The next thing that Dalton's atomic theory says is all the atoms of a given element have identical properties, including identical mass. Even this statement has, or this point has, its limitations, because today it is known that even atoms of the same element can have different masses. These are called isotopes. Like for instance, you have isotopes of carbon 12, 13 and 14. These are different masses. So this is again a limitation of Dalton's atomic theory. Now the third point here says atoms of different elements differ in mass. This is to say that different elements have their own atoms, and these atoms of different elements differ in mass. And again, this also has its limitations because today it is known that atoms of different elements do have the same mass. Like in the case of argon, potassium and calcium, you know that these are called isobars, and they have the same mass. Then the fourth point here says compounds are formed when atoms of different elements combined in a fixed ratio. Now, this is very much in accordance with the law of definite proportion. Compounds are formed when atoms of different elements combine in a fixed ratio. And then the last point here says chemical reactions involve reorganization of atoms. That is, whenever a chemical reaction takes place, reorganization of atoms takes place. And it says these atoms are neither created nor destroyed in a chemical reaction. Now this is again in accordance with the law of conservation of mass. But actually, Dalton's atomic theory says nothing about these bondings, or I should say bonds, chemical bonds that are there between the atoms that keep them together. Okay, so this is all about Dalton's atomic theory. Now, next we shall go on to atomic mass. Now, before we start talking about atomic mass, the first thing is, let's see what is an atom, and we shall also see what is a molecule. An atom is the smallest particle of an element which may or may not have independent existence. This is what is said about an atom today. So an atom is the smallest particle of an element which may or may not have independent existence. Now when I say an atom may have independent existence, then you can think of the atoms of these noble gases like helium, neon, argon and so on. So atoms of these noble gases, they can sort of exist independently. That's the meaning of atoms may have independent existence, or atoms may not have independent existence, like atoms of elements other than the noble gases. They cannot exist independently. They are always found in the combined state in nature. Like if you say hydrogen, an atom of hydrogen cannot exist independently. It is always found in the combined state. Or you can think of, say, sodium, for instance, an atom of sodium cannot exist independently as such. It is always found in the combined state in nature. So that's the meaning of an atom may not, atom of an element may not have independent existence. And the next thing is about a molecule. A molecule is the smallest particle of a substance. The substance here may be an element or a compound which has, that is, a molecule is the smallest particle of a substance which has independent existence. So that is, these molecules, they can exist independently. And here you can think of a molecule of dihydrogen, that is H2, hydrogen gas. One molecule of dihydrogen, a hydrogen gas, can exist independently. Likewise, one molecule of water, H2O, it can exist independently. So that's the meaning of independent existence. Now, next, moving on to atomic mass. Now, let us see what is this atomic mass. The mass of an atom is called its atomic mass, and the mass of an atom is expressed in terms of atomic mass units, and it is denoted by AMU. AMU stands for atomic mass unit. Then, now, let us see what is this one atomic mass unit. One atomic mass unit. One atomic mass unit is defined as a mass exactly equal to 1/12 the mass of an atom of carbon-12. 1/12 in the sense the mass of an atom of carbon-12. An atom of carbon-12 has its mass. When you multiply by 1/12, or that is when you when you divide the mass of one atom of carbon-12 by 12, then the mass you get there is called one atomic mass unit. So now I've written it here. One atomic mass unit is defined as a mass exactly equal to 1/12. That is 1/12 the mass of an atom of carbon-12. Right? And now, the mass of an atom of carbon-12 has been found to be 19.92648 into 10 raised to the power negative 24 grams. So this is in fact a very, very small number. It's because 19.9264 into 10 to the negative 24 grams. Negative 10 raised to the negative 24 means you're going to divide this number by 1 followed by 24 zeros. So this is going to be a very, very small number. So this is actually the mass of just one atom of carbon-12. Now this mass, that is the mass of an atom of carbon-12, when divided by 12, right, or when multiplied by 1 by 12, you are dividing by 12, you get this value 1.66056 into 10 to the negative 24 grams. So this value here, it is taken as 1 AMU. It is taken as 1 AMU. So this 1 AMU, 1 atomic mass unit, is nothing but 1/12 the mass of an atom of carbon-12. Now the mass of an atom of any other element is relative to this standard. That is, the mass of an atom of any element when divided by this number here, which is 1/12 the mass of an atom of carbon-12, will give you the relative atomic mass of that element. So now let's take up an example here. See, we say that the mass of an atom of hydrogen is 1 AMU. That is, we say that the mass of an atom of, that is, the atomic mass of an atom of hydrogen is 1 AMU. Why is it so? It is because now we have to find the relative atomic mass of any element. Relative atomic mass. Is equal to mass of one atom of the element divided by, we write 1/12 the mass of an atom of carbon-12. So to find the relative atomic mass of any element, you write the mass of one atom of that element and divide it by 1/12 the mass of an atom of carbon-12. Now this 1/12 the mass of an atom of carbon-12 is nothing but 1.6056 into 10 raised to the power negative 24 grams. That's it. So this mass, that is 1/12 the mass of an atom of carbon-12, is called 1 AMU. Now let's find the relative atomic mass of hydrogen atom, right? Hydrogen. Relative atomic mass of hydrogen. Now, it is known that the mass of an atom of hydrogen is, that is, the mass of one atom of hydrogen is 1.6736 into 10 raised to power negative 24 grams. Now this has to be divided by 1/12 the mass of an atom of carbon-12. So 1/12 the mass of an atom of carbon-12 is 1.66056 into 10 raised to power negative 24 grams. Now when you simplify this expression, gram and gram will get cancelled. Negative 24, when you take it on top, it becomes positive 24, they get cancelled. So it is 1.6736 times power negative 24 into 10 to the power, it becomes positive 24, the whole divided by 1.66056, right? These two, they become 0 and it is 1. It becomes 1, right? They get cancelled. So when you divide 1.67036 by 1.66056, you're getting 1.0078 approximately. And we take this as, okay, 1 AMU. So we say that the mass of an atom of hydrogen is 1 AMU. This is approximately, it's approximate value, right? 1 AMU. Now the meaning here is the mass of an atom of hydrogen is almost or equal to 1/12 the mass of an atom of carbon 12, that is 1.605 10 to the power negative 24. And this is because hydrogen is the lightest element, and an atom of hydrogen is the lightest among all atoms. So this is 1 AMU. This is the meaning of any relative atomic mass of an element. So this expression you're supposed to know. Now, based on this, we shall move on to the next part, and that is now we're going to talk about something called the average atomic mass. Average atomic mass. Now, before we talk about this average atomic mass, I want to make one thing clear, that is, instead of 1 AMU, today we write 1 U, that is U stands for unified mass, right? So instead of AMU, you can write U, which means unified mass. Okay, just keep that in mind. Now the next thing we're going to take up is average atomic mass. Average atomic mass. Now, many of these elements, they exist in the form of 2 or more elements. 2 or more isotopes. So, many of these elements, they exist in the form of 2 or more isotopes. So based on their existence and abundance, we find what is known as the average atomic mass. Average atomic mass. Now, when I say average atomic mass, it is actually the average of the masses of the isotopes of these elements. Now, one example I can give you is that of carbon. See, you have, let's take the first example, right? Isotope here, then I have relative abundance in percentage, right? Relative abundance, and then it is you have atomic mass here, atomic mass. Now talking about average atomic mass, you know that the isotopes of carbon are carbon 12, you have carbon 13, then carbon 14. And their atomic masses are, carbon 12, it is 12, carbon 13, it is 13.0035335, and then that of carbon 14, it is 14.00317. And then the relative abundance in the case of carbon 12 isotope is 98%. Carbon 13, it is 1.108%, and that of carbon 14, it is 2 into 10 raised to the power negative 10%. Very small number here. All right. So now, to find the average atomic mass of carbon in general, we take the percentage of each of these isotopes that occur in nature. So the carbon that exists in nature, in a sense, in the form of isotopes, carbon 12, carbon 13, and carbon 14. Now their abundances are carbon 12, 98%. 98% of carbon in nature is carbon 12. 1.10% of carbon in nature is carbon 13, and the carbon 14, it is very small amount, right? So now what we do is we just add up all these by calculating. See, 98% of carbon 12. So I write average atomic mass of carbon. Average atomic mass of carbon is 98% of this mass. So 98% means by 100 into 12 plus 1.108% means divided by 100 into this mass, 13.00335 plus 2 this percent, right? That is 2 into 10 raised power negative 10 again by 100 into this, that is 14.00317. And here the values turn out to be, in this case, it has been found to be something like 11.87. You can calculate it yourselves later. And here the next one, the value here is found to be 0.144 plus here the third one, when you simplify this 10 to the negative 10, when you bring it down, it becomes 10 to the positive 10, 11, 12. So this 2 has to be divided by 1 followed by 12 zeros and then multiplied with that. So it's going to be a very, very small number. It is almost equal to 0, right? Some number. And finally, when you add up all these, you are getting 12.011 U. That is unified mass, as I told you. And we generally say that the atomic mass of carbon is approximately 12 unified mass. This is the meaning of average atomic mass. Likewise, another example I can give is that of, say, chlorine. Chlorine has 2 isotopes, right? Chlorine 35 and 37. Chlorine 35 and 37. So the relative abundance of chlorine 35 is found to be 75%, and that of chlorine 37, it's 25%. And here the mass, atomic mass of chlorine 35 is 35, and that of 37 is 37. And when you work it out, so the average atomic mass of chlorine, is equal to, now again you take the percentage of these and you will get the average atomic mass of chlorine. Now the atomic mass of the elements that you see in the periodic table are the average atomic masses of these elements. So here it is 75%, the first one, 75% of chlorine 35, and then the next one it is, plus, I'll add up these, plus 25%, 25 by 100 into 37. When you work it out here, you're getting, this is 0.7, finally it becomes, let me just write, 26.25 plus this one here is 9.25, and the sum of these two is 35.5 unified mass. So now this is the average atomic mass of chlorine. So this is the meaning of average atomic mass, and this is how the average atomic mass of different elements are actually calculated. So it is based on their existence and their abundance. Okay, so that's all about average atomic mass. Now, the next thing that we're going to learn is about molecular mass. Now, just like you've seen atomic mass, we now talk about something called molecular mass. Now, as far as molecular mass is concerned, it is nothing but the sum of the atoms, that is sum of the masses of the atoms of different elements present in a molecule. So you just have to find the sum of the masses of the atoms of different elements that are present in a molecule. So let's see, this is the molecular mass. The sum of the masses of the atoms of different elements present in a molecule is called the molecular mass. Now we'll just take up an example, like the simplest one I think is that of water. We'll try to find the molecular mass of water. Now you know that the mass of an atom of hydrogen is 1, you see. And here, since you have 2 atoms of hydrogen in a molecule of water, what we do is, 1 is the atomic mass of 1 atom of hydrogen, and since you have 2 atoms there, you multiply by 2 plus 1 atom of oxygen. So an atom of oxygen, its mass is 16. The sum of these two is 2 plus 16 is equal to 18. You write U here, this is the unified mass. So this is the atomic mass of a molecule of water, H2O. Likewise, now you can easily find the molecular mass of any other molecule. Like if you take up carbon dioxide, again the molecular mass of carbon dioxide, say 1 atom of carbon, the atomic mass of carbon is 12 and that of oxygen, it is 16. Since there are 2 oxygen atoms, it is 16 to be multiplied by 2, and then you have 12 plus 16 to 32. It is now 44 unified mass. So this is the molecular mass of carbon dioxide. Likewise, you can just calculate. Now maybe you can find the molecular mass of methane. You can find the molecular mass of, say, glucose, C6H12O6. You can find the molecular mass of, let's take H2SO4. And so on. So you can take up many more examples. Like in the case of sulfur, the atomic mass of sulfur is 32. So just add up all these, and then you will get what is known as the molecular mass of these molecules. And next, we have something called the formula mass. Formula mass. Now, why this formula mass? It's because in the case of ionic compounds, like for instance, sodium chloride, it is NaCl. It is said that these entities like sodium chloride, NaCl, they do not exist as discrete molecules. They are always found in the combined state. Sodium chloride, they cannot exist discretely or independently, like in the case of these molecules, covalent molecules. That is why it is called the formula mass. Formula mass. Right, it's the same thing. To find the formula mass of a compound like any compound, like sodium chloride, let's take NaCl. These are ionic compounds. So in the case of ionic compounds, you will call its mass, the mass of one entity, as the formula mass. In the case of these covalent molecules, when I say covalent molecules, you have sharing of electrons. There is no positive charge, negative charge on these atoms as such. But in the case of ionic compounds, you have separate positive and negative charges. So these are called ionic compounds. So in the case of ionic compounds, their mass, it's called the formula mass. Now, if you have to find the formula mass of sodium chloride, we know that the atomic mass of sodium is 23 and that of chlorine it is 35.5. Add up these two, you get it's 58.5. Put U here. So this is the formula mass of sodium chloride. Likewise, you can find the formula mass of many other ionic compounds. Like if you want, you can take up let's take sodium carbonate. Now here, this is sodium, 1 atom of sodium, its atomic mass is 23, carbon is 12, and you have 3 atoms of oxygen, so it is 16 into 3. it's going to be 23 plus 12 plus 6 and 3 is 48. When you add up all these, you're going to get 50, 60, 70, 83 if I'm not wrong. 6.8, 12, huh? Okay, 50, 60, 70, 83, it's 83 unified mass. So this is all about formula mass. And now the next thing that we're going to take up is mole concept and molar mass. Mole concept and molar mass, right? So now the next subtopic that we're going to take up is mole concept and molar mass. Now, the quantity or the amount of a substance is expressed in terms of mole, and the unit of this amount of substance, that is the SI unit of the amount of a substance is mole, M-O-L-E, mole, and the symbol for this SI unit mole is M-O-L, right? Now, let us see what is this 1 mole. So how do you define 1 mole? 1 mole is defined as the amount of a substance that contains as many particles or entities as there are atoms and exactly 12 grams of carbon-12 isotope. Now you have to think very deeply. So the amount of a substance that contains as many particles or entities as there are atoms in exactly 12 grams of carbon-12 isotope is called 1 mole. And now this number is 6.02 to 10 raised to the power 23. 6.02 to 10 raised to the power 23. Now you may wonder how we get this number. And in fact, this number is so very important that it is given a separate name and a symbol. It's called the Avogadro constant, and it's denoted by N-A, capital letter N-A. Right? Alright. Now, we know that the mass of an atom of carbon-12 in grams has been found to be 19.92648 into 10 raised to the power negative 24 grams. This is the actual mass of an atom of carbon-12. And now, when you take exactly 12 grams of carbon, very simple. This number here is the mass of an atom of carbon-12, and it is nothing but the mass of an atom of carbon-12. One atom of carbon-12 has this much mass. Now, 12 grams of carbon will contain how many atoms? This is what you have to find. Now look at this. This is very important. So this is sort of direct proportion relationship here. So 19.92648 into 10 raised to the power negative 24 grams is equal to 1 atom, if this is 1 atom. Then when you have 12 grams of carbon-12, then how many atoms? So since it is direct proportion relationship here, you just cross multiply this way. So I'm going to get x here and multiply these two. See, I write x here, multiply these 12 grams into 1 atom of carbon-12. Here you have this atom here. And then this number here will come down here in the denominator. Now when you simplify this whole thing, gram and gram get cancelled. And to come here, this is 12 into 1 atom of carbon-12, this number here. Now, this is 19.926. I've made this 1.99. Here I have changed this expression by bringing the decimal point to the left by 1 digit, right? So, I'll have to multiply this by 10 and it becomes 10 raised to the power negative 23. So finally, you're going to take this 10 raised to the negative 23 on top, it becomes 10 raised to the power positive 23. It is atoms here, and 12 divided by 1.9 and 2648. And when you simplify this expression, you're going to get 6.02 to 10 raised to the power 23 atoms. There's a number of atoms in 1 mole. Now, 12 grams of carbon is taken as 1 mole. So in 1 mole of carbon, you will have 6.02 to the 10 power 23 atoms of carbon 12. So this is how you get this number. So now 1 mole of any substance for that matter. Now suppose you have 6.022 into 10 raised to the power 23 atoms of sodium. This is 1 mole. Or 1 mole of sodium will have 6.02 to 10 to 23 atoms of sodium. Now if you consider say dihydrogen, that is hydrogen gas, when you have 6.022 into 10 raised to the power 23 molecules of hydrogen, then this is again, we call it 1 mole. Now how do you get this? This is actually obtained from what is known as the molar mass. Molar mass. So when I say molar mass, it is nothing but 1 mole of any substance expressed in grams is called the molar mass, right? So when 1 mole of any substance is expressed in grams, it is called molar mass. So 1 mole of a substance expressed in grams is called its molar mass. So let's see. If you take, for example, 1 mole of oxygen, then here you will see that 1 mole of oxygen has 6.022 into 10 raised to the power 23 atoms of oxygen. Say if you take atoms of oxygen and if you take molecules of oxygen, then you will have 6.02 to the 10 raised to the power 23 molecules of oxygen. So based on the molar mass, let's see, you will take any example. For instance, we'll take what? Molar mass of, let's take sodium. You know sodium, its molar mass. The atomic mass of sodium is 23 unified mass. Now if you take its molar mass, it is 23 grams. 23 grams. So now what we actually need to do is the number of atoms of sodium in 23 grams of sodium is 6.02 to 10 raised to the power 23. Let's see how we get this. This is 1 mole, right? 1 mole. Now, the mass of an atom of hydrogen, the mass of an atom of sodium, it is based on its atomic mass. See, we know that the atomic mass of sodium is actually 23 unified mass. Now this actually means the actual mass of an atom of sodium is 23 times 1/12 the mass of an atom of carbon 12. This number unit is 1.66056 10 raised to the power negative 24 grams. So this is the mass of one atom of sodium. So now let's see. When 23 into 1.66056 into 10 raised to power negative 24 grams is equal to 1 atom of sodium. Then when you take 23 grams of sodium, what is the number of atoms here? You put X. So you just cross multiply. It is okay. Alright, X here. This is equal to 23 grams here into 1 atom of sodium, right? Divided by again 23 grams. Sorry. 23 1. 23 into 1.66056 into 10 raised power negative 24 grams. They will cancel. And when you simplify, it is finally 23 divided by 23. Okay, it is 1. And you have this as, there's a negative 24, you can take it top. So here I'm left with 1 into 10 raised power. This becomes positive 24 atoms, right? And divided by this is 1.66056. So when you divide this by 1 by this number 1.66 or whatever, your value here is going to be 0.6022 into 10 raised power 24 here. This is 24 atoms. Now if you write this in the scientific notation form, this becomes 6.022 into 10 raised power 23. You got it? I hope you got it. So this number is once again fixed. In the case of sodium, when you take exactly 23 grams of sodium, you will see that there are 6.02 times by 23 atoms of sodium. Now if you want, you can try for any other atom, that is any other element, or you can try for any molecule, or for any entity or any species, should I say. Like we'll consider for oxygen, let's see, oxygen, right? Now we know that the molar mass of, that is oxygen here, it is 32. Each oxygen atom is 16, so this is 32 grams. You've got to take it in terms of grams, right? 32 grams. This is actually in terms of molecules. So now how many molecules are there in 1 mole? This is 1 mole. So now the molar mass of oxygen gas is 32 grams. It is called 1 mole. Now we need to know the mass of 1 molecule of oxygen, right? Mass of 1 molecule of oxygen. It is now it is based on the molecular mass. See, the molecular mass of oxygen is actually okay, let's take it this way. Molecular mass, it is 32 unified mass. This actually means it is 32 into 1.66056 to 10 raised power negative 24 grams. This is the actual mass of 1 molecule of oxygen in grams. This is the molecular mass, right? So the mass of 1 molecule of oxygen, 32 unified mass. So now let's see. 1 molecule has this mass, right? So I put it this way: 32 into 32 into 1.66056 into 10 raised power negative 24 grams is 1 molecule of oxygen. Now when you have 32 grams, this is the mass in grams of just one molecule of oxygen. And when you have 32 grams of oxygen, this is equal to how many molecules? Let's take it as x, and when you cross multiply, you will get x is equal to, this is 32 grams into one molecule, right? This is in terms of molecules. We'll get the final answer in terms of molecules. So divided by, this whole thing comes down, 32 grams into 1.66056 in 10 raised power negative 24. Alright? The grams I should write it there. Yeah, 32 into. I put gram here. Gram and gram get cancelled. This is 1. So once again, you are getting the same thing. This is equal to 1 divided by 1.66056. This will go on top into 10 raised power positive 24 molecules. So this, when you divide 1 by this, you will get 0.6022 into 10 raised power 24 molecules, right? I put it this way, molecules. Or when you write the scientific notation, 6.022 into 10 raised power 23 molecules per mole, right? That is in 1 mole per mole. That is in 1 mole of dioxygen, you will get what? 6.022 into 10 raised power 23 molecules of oxygen. Similarly, you can do the same calculation for, say, water. You will see that the number of molecules of H2O in 1 mole of water, that is, in the case of water, H2O, it is 18 unified mass. This is the molecular mass of water. So when you take exactly 18 grams, this is 1 mole, right? This is 1 mole. Now you will again find the mass in grams of 1 molecule of water, and then you divide this 18 grams by the mass of 1 molecule of water in grams, and you will get this number. Now this, and you can try yourself, right? Okay, that's it. Now we shall work out some numericals or problems based on what we saw just now. Let's see. Now the most important thing here is to know that, see, you may wonder how can one get the mass of an atom of an element in grams. See, one example I can give. See, you know that the atomic mass of hydrogen, we say it is 14 unified mass, right? This 14 here means, in terms of grams, 1 unified mass, that is 1 atomic mass unit, it is nothing but 1/12 the mass of an atom of carbon-12, and that, it has been found to be 1.66056 into 10 raised power negative 24. So when you multiply this 14 into 1.66056 into 10 raised power negative 24 grams. This will give you the mass of 1 atom of nitrogen in grams. This is in grams. This is the relative atomic mass. This is to say that the mass of an atom of nitrogen is 14 times 1/12 the mass of an atom of carbon-12 isotope. Now in terms of grams, you multiply this 14 by this number. Another example, like see, if you take H2, hydrogen gas, what is the mass of 1 molecule of hydrogen? Now we know that the molecular mass of dihydrogen is 2 unified mass, right? So you multiply this 2 by, 2 into 1.66056 into 10 raised power negative 24 grams. So this will give you the mass of 1 molecule of hydrogen. So using this technique, you can easily find many things here now. So let's see, we'll just try to work out a few numericals. The first one, now I'll try to make it a little faster. Okay, I'll explain these things. Now we know how to find the molar mass. Now next, let's see. Find the number of moles of sodium hydroxide in the following. This is simple. Find the number of moles of NaOH, sodium hydroxide, in the following. Now you know the meaning of molar mass, right? Now I'll give some examples here. The first one is, let's take 100 grams. The second one, that's 100 grams of sodium hydroxide and 10 grams of sodium hydroxide. The third one, you have, say, 2 kg of sodium hydroxide, and the fourth one, say, 1.6 kg of sodium hydroxide. Very simple. Very simple. This is solution number 1. The first one, let's say it is 100 grams of sodium hydroxide. Now we want to know how many moles of sodium hydroxide are there in 100 grams of sodium hydroxide. Now we know the molar mass of sodium hydroxide is what? See, molar mass of sodium hydroxide, that is 1 mole of sodium hydroxide. Sodium is 23, oxygen is 16, and hydrogen is 1. When you add up all these, you're going to get 40, right? And when you express this in terms of grams, it is the molar mass. So now we know that this is 1 mole. This is 1 mole, right? So now 40 grams of sodium hydroxide is equal to 1 mole. Now when you have 100 grams of sodium hydroxide is equal to how many moles? You put x here, just cross multiply, and then you will get x is equal to 100 grams up there into 1 mole here, divided by, this whole thing comes down, it is 40 grams. So gram and gram get cancelled. And finally 2 2s are 2 5s 10. This is equal to 5 by 2 is, I think, 2.5 moles, right, of NaOH. Very simple. So here, in 100 grams of sodium hydroxide, you will have 2.5 moles of sodium hydroxide. It is simple. And the next one, 10 grams, you can try it out yourself. And I'll just move to the fourth one. The other two you can try out yourselves. Let's see. The fourth one is given in terms of kilogram, right? So we'll just see. You're given 1.6 kg of sodium hydroxide. So in this, how many moles of? Okay. Now again, you know that the molar mass of this thing, sodium hydroxide, is 40 grams. So you know 1.6 kilogram, you should convert that into grams. So we know that 1 kilogram is 1000 grams. So when you have 1.6 kilograms, this is equal to how many grams? Cross multiply. It is equal to 1.6 kg into 1000 grams. Very simple, all of you know actually. Okay, kg get cancelled. Just multiply 16000. Okay, it becomes 1600 grams. This is 1600 grams. So now what we're going to do is, when you have 40 grams of NaOH, this is equal to 1 mole, we call it 1 mole. And when you have 1600 grams of NaOH, this is equal to how many moles? Cross multiply, H is equal to 1600 grams into 1 mole divided by this 40 thing comes down here, 40 grams, they get cancelled, 0 0 for once, 4 4 16 0, so the H is equal to finally 40 moles. So this means you're going to have 40 moles of sodium hydroxide in 1.6 kilogram of sodium hydroxide. So this is all about finding moles. And now the next thing is with regard to find the number of atoms of sodium in the following. Finding the number of atoms. So the next question, the number of atoms of sodium in the following. You have 5 moles of sodium, the second one 2.5 moles of sodium, the third one 46 grams of sodium, and the fourth one 1.15 kg of sodium. Very simple. Alright, so this is the second question. Very first one is 5 moles of sodium, right? Now we know that 1 mole of sodium contains 6.022 into 10 raised power 23 atoms, right, of sodium. So when you have 5 moles of sodium, okay, it contains how many atoms? Take as x, cross multiply, your x is equal to 5 into 6.022, 10 to the power 23 atoms of sodium divided by, okay, yeah, 1 mole, this is 1, you have to write this, put this down here. This is actually 5 moles, yes, sorry, this is 5 moles. So mole and mole get cancelled, and finally just multiply these two, so it becomes 5 to the 10, yeah, 1 remains, 10, 11, okay, 1 here, and then 5 to 30, something like this, I'm right, 10's power, 23 atoms, this is up to 3, 1 to 3, 30 point something here. So this is finally equal to 30.110 into 10 raised power 23 atoms of sodium. Or if you write this in the scientific notation form, this is 3.0110 into 10 raised power, make number smaller, 24 atoms of sodium. So in 5 moles of sodium you have this many atoms of sodium, and then you can do the same thing for the rest. And the last one, the fourth one, I should try it. Okay, let's see. You have 1.15 kg of sodium. 1.15 kg of sodium, right? So you know that the molar mass of sodium is 23 grams. So now here what I need to do is just convert this into grams first. So for this you'll have to multiply by 1000. 1.15 into 1000 is 3 zeros, 511. So 1150 grams. So this is the same as 1150 grams of sodium. This is equal to how many moles, right? Now see, in the case of sodium, you know that 23 grams is 1 mole. You see, 23 grams of sodium is 1 mole, and now when you have 1150 grams of sodium is x moles. Cross multiply your x is 1150 grams of sodium into 1 mole divided by 23 grams here. Okay, finally this is 23, I think it is 23, 5 times 150 we get, and then 0 here, x is equal to, this is now 50 moles of sodium, right? 50 moles of sodium. Now we know that, what we know is, we know that 1 1 mole of sodium is equal to, or it contains 6.022 into 10 raised power 23 atoms of sodium. And when you have 50 moles, so 50 moles of sodium is equal to how many atoms? Again, you just cross multiply. X is equal to 50 moles into 6.022 into 10 raised to power 23 atoms divided by, okay, 1 mole here of sodium. So mole and mole get cancelled. Finally, when you multiply these, you will get 1 0 there at the end. Then 5 2 is 10. 5 is 10, 11, 1 remains. 1, 5, 6, 30 into 10 raised power 23 atoms. 23 atoms. And now the decimal point comes after 3 digits from the back 1 to 3 here. This sum here. And if you write in the scientific notation form, it becomes 3.01100 into 10 raised to power 25 atoms of sodium. Alright, that's it. So now this is all about the number of atoms of sodium present in these different quantities of sodium. Alright, so with this I'll stop here for today, and then I have some more calculations to be done, plus another subtopic, that is percentage composition. Now should I say shortage of time, I'm not able to complete it today, so I'll sort of complete it in the next lesson in part 3. Thank you very much. Thank you.